Thank you for joining me for this video. I am Mr. Ish. It's a very interesting topic and concept today. You know, b to the x, it's a power function style of function. We have to evaluate it in terms of development for a power series at a equals 0 and then analyze that power series for convergence. That a equals 0 tells you everything you need to know. We're looking here at a Maclaurin series, which is originally part of a Taylor series centered around 0. It's not hard. You have a function which will develop in terms of a power series representation, as I will show you. N equals 0 up to infinity. You will have the nth order derivatives receiving the 0 value, which is your a. N factorial and x to the power of n. The minus a is converted into just x to the power of n because 0 is coming into place of a. You have to determine at least a good number of derivatives, higher order derivatives for that function. And it's not a hard one by any means. The 0 order derivative is equal to the original function, which is b to the x. Your first order derivative is b to the x ln b. And then you're doing the derivative of each of these. Your second order derivative would be b to the x, and this would serve as a constant, and you're just doing a derivative of that. You'll have ln b times ln b, it'll be ln square b. Your third order derivative, you know that, you'll do the derivative of that previous step. You'll do b to the x, you'll have ln cube b, because in each case this serves as a constant and you're just doing a derivative of this. It brings in a new natural log b value and the b to the x stays as is. The fourth order is b to the x ln to the power of 4b, and the fifth order is b to the x ln to the power of 5b. But in each of these areas where you're seeing an a value equals 0, it's going to come into places of x. In all of these instances, these b to the power of 0 will become 1. You'll only have the natural log components remaining after that 0 derivative. Everything else is easy. This will just become here a 1, this here will just become that will just become that, and that. Everything else will become a 1. B to the power of 0 is always equal to 1. What will your series be? If you're analyzing your series, you're looking at everything now in terms of a Maclaurin polynomial. I'm going up to 5. And we'll develop the fifth Maclaurin polynomial for this power function. It will be composed of 6 terms, starting with 0, n equals 0, and then you do all the way up to n equals 5. You'll have 6 terms because it's always n plus 1. Anyhow, that's a rule for when n is equal to 0. Let's do it. What's the first item? The first item is going to be 1 times x to the power of 0 divided by 0 factorial. The next item is going to be this, just the natural log b. Natural log b x to the 1 over 1 factorial, then natural log square b x to the 2 over 2 factorial, and then after this we'll have natural log cube b x cube over 3 factorial. Here we have natural log to the power of 4 b x to the 4 over 4 factorial, and last item will be natural log to the power of 5 b x to the 5 over 5 factorial. You've seen how all of these derivatives have come about. There's nothing surprising over there. The derivative of the power function is easy. When you're doing a equals 0, all of these variable components become 1. You're just left with the constants which fill in. So we've come up to this point. All of this represents exactly this. m5x, your fifth polynomial of the Maclaurin series related to this function right here, a equals 0. You can clearly see the trend over here, and you can clearly come up with a power series. Your power series would look like this. It's going to have always a x to the power of n. You'll have here natural log b to the power of n, and then you'll have n factorial. And if you want to be a little bit more careful here, from n equals 0 up to infinity, that'll be a power series for this function right here, and it should be good. You can test it out for the first 1 or 2 terms just to make sure everything is good. When n is equal to 0, you'll have x to the power of 0, natural log b to the power of 0 over 0 factorial. What will this give you? It will give you exactly what you have over here, which will be a 1. When n is equal to 1, you'll have x to the 1, natural log b to the power of 1 over 1 factorial. It will give you x natural log b over 1 factorial, which is this. When n is equal to 4, in here you'll have x to the power of 4, natural log to the power of 4b divided by 4 factorial, which is exactly that. So we know we are on the correct page. So we've developed the power series. We have to develop the power series. We've developed it using the Maclaurin route, going as high as this, but you'd keep adding more n terms. Now we have to analyze this for convergence. How are you going to do it? The ratio test. Look at your a n plus 1 term in absolute value. This right here is your series. You'll evaluate it by the ratio test. You'll have x to the power of n plus 1. You'll have natural log b to the power of n plus 1 divided by n plus 1 factorial. Now you look at your nth term. It's exactly that, x to the power of n, natural log b to the power of n divided by n factorial. You're looking here at the ratio of these. It's not hard. I've brought my power series right here and I've opened up the space. Open this up using algebra. You have x to the n, x to the 1 times natural log b to the power of n, natural log b to the power of 1 divided by this. You know this in terms of a shortcut is n plus 1 times n factorial. I've shown you that in one of the videos. Multiplied by the reciprocal of this. Here you'll have an n factorial, here you'll have x to the n, natural log b to the power of n. Cancel out your terms. This cancels out, that cancels out, that. Natural log b to the n cancels out with this. What are you left with? You're left with natural log b, you're left with this, and you're left with that. Let's write it out in a good way. We'll have natural log b times absolute value of x. This I'm combining with this. Limit as n approaches infinity. I have a 1 over here, and I have this n plus 1. That's very easy. When you evaluate this right here, this part will always equal to 0 if you do a horizontal asymptote style of determination or a basic limit evaluation. That's equal to 0. You're looking at natural log b times absolute value of x times 0. All of the zeros out. What does that tell you? It tells you regardless of the value of this variable here, your limit and your function over there with regards to n will always approach 0. Everything will always approach 0. So you'll always have convergence for this power series for all values of x. What does that tell you? You have a radius of convergence equal to infinity. If you have a radius of convergence equal to infinity, meaning your power series is convergent for all values of x, you have an interval of convergence which looks like this. X is less than infinity, greater than minus infinity. Or you can write it as minus infinity to positive infinity, and that right there would be your answer. You can verbalize everything as by saying that this power function series right here, which represents b to the x in a power series form, is convergent for all values of x. Radius of convergence infinity, interval of convergence right over here, and you're done. And that's all I wanted to show you for this particular video. See how everything came out with the easy higher order derivatives coming into an easy form of a Maclaurin polynomial, which represents your series, from which you can determine your series rule, which is your power series, from which via the ratio test you can come up to this conclusion of infinity with regards to your radius of convergence and interval of convergence. Thank you. Have a good day.